All right. Grace, let's begin with you. You had a question, and I figured other people might have the question, so I
Okay.
thought we would just start there.
Okay. You want me to ask it?
Yeah, yeah, so
Okay.
everybody else can hear.
Okay. Um, I for each problem I've done everything up to finding the sums of squared for the residual.
Mhm.
And I guess like just looking at the equation and everything, it's hard to understand and apply that to my data.
Okay.
Um, Using like the little y subscript j and y subscript I stuff, I
Hmm.
just don't know which one those are.
And so you're having the most trouble with the unreplicated data set, right?
Yeah.
Okay. Yeah, and the unreplicated data set is actually the more difficult one to work on because it's not arranged. The equations are somewhat different because it's not replicated. And so this is actually kind of a good sign because you've gotten used to calculating residual sums of squares by taking the individual data points within a treatment and comparing it to that treatment mean. So and then an unreplicated design forces you to do something different, and that's throwing you. So in a way, I'm kind of glad that you're having a little more difficulty with that, but let's make sure that we can figure it out so that you can complete your assignment. So I've pulled up the price data set here.
Hmm.
Can everybody see my spreadsheet?
Yeah.
Okay, so when we click on this, so this is calculating sums of squares total. When we click on that, what we have here is this is the difference between the grand mean, which is 2.459, and the individual data point squared. So this is a form of sums of squares, and it's the individual values minus the grand mean squared. And hopefully you were able to calculate that correctly.
I haven't done that yet.
Okay, so that's in that way, sums of squares total is very much like sums of squares total in a regular two-way ANOVA. I have,
Okay.
pardon me, I have a separate sheet here for sum of squares residual. And in this case, this is basically the individual value minus the column mean minus the row mean plus the grand mean. And then that is squared. And that's very unusual in terms of the kinds of calculations that we've done in the past.
Okay.
So in the price data set, you need to look carefully, click in the formula bar of that second sheet that is entitled sum of squares residual. And on any of these, it's going to always be, whoa, what happened there? Oh, I'm over here. On any of these, it's always going to be the value minus the column mean minus the row mean plus the grand mean. And then that value gets squared.
Okay. Why does yours have like dollar signs? Oh, that's because it's the dollar. Yeah. Okay. Never mind. It's a
Yeah,
price.
it's for that row, everything. Wait, sorry, for that column, everything in this column is going to be done with 2.431. And so that just prevents me from having to
Okay.
type it in. Once I have it written this way, I can just grab this corner and drag down, and it will do the rest of the calculations.
Okay.
Okay. So when you go to row B, you'll see that once again it's C12, which is the column mean that is the fixed value, and then the row means change. And then rather than put in, I could have just as easily done this instead of putting in 2.459. I could have just as easily clicked on this and then put a $sign there and a $sign there, and that would fix it at the grand mean. So
Is that for residuals?
this is a residual sums of squares, yes, in the unreplicated two-way design.
So questions 1 and 3 or 1 and 4?
2 and 4.
2 and 4, yeah.
Those are the two unreplicated ones, if I'm recalling correctly. Does that answer all your questions, Grace?
Yes.
Okay, good. I figured we would be able to dispense with that pretty quickly.
Mhm.
So, does anybody have any other questions? On a side note, how are you guys doing with the whole social distancing thing?
I'm kind of just staying at home with my family, so we don't really
I'm kind
social
of the same.
distance from each other.
Yeah, for me, I'm coming into work because the whiteboard behind me is useful. But let's see, in the parking lot right now is my car. I'm the only one at Jewel.
I was going to
You're
ask
not-
if there are any other
you're not-
professors or anyone there.
Oh, so Athos, you're still on campus.
Me, Pedro, Asa, and Micah. Yeah.
Okay, yeah, but when I look out at the faculty lot, my car is the only car in the faculty lot, and there's no cars in the student lot down the hill from me. So I come in Monday, Wednesday, and Friday at the very least, and I don't see a soul while I'm here. How are the rest of you doing?
Doing good, just the same, staying at home.
Good. No illness in anybody's family?
Nope.
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 Good. Good. Well, it's good to hear. All right. I posted yesterday a screencast on regression. Did you guys get a chance to look at that? I was doing some edits on it, so it didn't get out as quickly as I wanted it to. But do you guys have any questions about that? Did the regression method seem to make sense to you?
Yeah.
Computationally, the regression isn't really difficult. Once again, one of the things that I want to always be stressing to you guys is the commonalities between all of these things. So things I want to go over with you in particular is this figure here, which is slide 16 if you're following at home. When we go about the process of actually testing to see if the regression is significant, which is basically asking the question of, is this slope different from 0? You see that the calculations that we go through to get to this are simply a bunch of sums of squares again. And so in this way, the regression model isn't really very different from an ANOVA model, and that you test for significance the same way. It's the sums of squares of the main effect divided by the the mean squared of the main effect divided by the mean squared of the residual, and that's the F statistic that you use to test on. And so let me go back to this is basically the data set on flower beetles. And the line is the best fit line through the data. But this is also, and this is a point that I want to stress again, I already said it in the screencast, but this line represents the running average of Y, mass loss in this case, as X changes. And so one of the ways of thinking about this is to think of this as the mean. It's just that the value of the mean changes in a constant way depending on what X is. And so when you look at the residuals around this, and we'll talk about this on Monday, when we talk about what the assumptions of a regression are, this distribution of residuals around the line, so we have some residuals that are larger and above the line, those are positive residuals. Some residuals that are close to the line but positive, those are small positive residuals. A really large positive residual here, two fairly big negative residuals here, and then some residuals that are very, very close to zero right along the line. This distribution of residuals around the line is the normality assumption. And so you can actually just save the residuals from this line and put that to a Shapiro-Wilk test to test the normality assumption. And so residuals are important not only for figuring these sums of squares out, which is what you need ultimately to calculate the ANOVA table, but those sums of squares or those residual values are also then useful in ascertaining whether or not you have data that are normally distributed in a regression sense, which is slightly different than the normality assumption in the ANOVA, but it's still the same idea. So you guys were able to follow the equations, or did you get a chance to look at the screencast?
Paul, this is Tom. I
Yeah.
looked at the screencast. The last in back to that spreadsheet you were just showing us.
Oh, yeah.
Not the ANOVA table, but the other one. The last column and the third to last column.
This column and this column?
I'm not seeing it on my screen.
Oh, let me make sure that I've got it back. Can you see it now?
That column and
That column.
Yeah.
Mhm.
Those. I get if you could just one more time describe the difference or the similarities, because I think in the video you use the word residual to describe both columns, which confused me.
Oh, did I? Oh, yeah, that was me misspeaking. So think of this column right here, the column called D. This is the individual values of Y, 8.98, minus the expected value of Y. So 8.98 minus 8.74.
Okay.
That's what this value is, 0.276. When you add all of those up, that sums to zero because all of the residual values sum to zero.
Okay.
So the whole reason that we square residuals when we're trying to quantify variation is so that we can get rid of those negatives so that they don't sum to zero and they sum to something that has value. This is basically, the reason I talked about this as a residual value is that once again, it's something minus something that should be centered on the mean. So this is the predicted value, which is what Y hat is. Y hat, okay. Normally we would write, can you guys see my screen?
Yeah.
So normally we would write this Y hat. If you ever see this thing in a statistics textbook, this is the predicted value. And this is the value that is predicted by the regression model that we generated. The slope of negative 0.053 times x plus the y-intercept. So this is what comes out of y equals a plus bx, and whatever a and b is, and whatever x value is, this is what gets predicted. But you also have what is observed, and so the mean is what is observed. And going back, so this y hat minus y bar isn't this figure, because these are the residual values from the individual values to a hypothesized slope of 0. This is the difference between where that line intersects the best fit line and a line of 0. So you're testing to see if this model is significant. If the model is significant, then the model will describe a lot of the variation that is in the data that is due to the model. Well, what is the variation that is due to the model? It's the difference between the predicted value of the model and the average value of the y variables. And because you have the predicted value that is big and above compared to the mean, predicted value big and above compared to the mean, predicted value big and above compared to the mean, predicted values large and negative compared to the mean, predicted value large and negative, predicted value large and negative, predicted value smaller and negative. Those predicted values, because it's all symmetrical, centered on this fulcrum point in the middle, which is the mean of relative humidity versus the mean of mass loss. That's where this line should pivot. Then you're going to have the same magnitude of values that are positive and the same magnitude of values that are negative. And so as we blow through all of this and we get to this column is how does this value 8.704 differ from 6.022? And so it's
help me read the column title of that column.
Yeah, so this is taken. So the problem with doing this in Excel is Excel doesn't allow you to do equations and things like this. And so it's basically y hat minus y bar. So it's the predicted value 8.704 minus y bar, which is this value, which is just the sum of all the y values divided by the number of values that you have. It's just the average of y, which is the average of weight loss, which is 6.022. So that's 8.704. 8.704 minus 6.022. And you
So
see
what,
that's
but back to the
2.682.
column, but back to the column title.
Yes.
What is it? What is that? It's y and the hat minus y hat minus.
No, it's confusing. Let me just fix it. The actual calculation is, the actual calculation is just,
Oh, okay.
is just this.
Got it. Okay, good.
Yep, that's all it is.
I'm good.
And then what you see is that whole thing sums to 0. So in this way, it's basically a type of residual. It's a type of numerator of a variance without squaring it to truly make it the numerator of the variance, the sum of squares, you have to square all of those things, and that then becomes the sum of squares. That is the measure of the variation that is due to the data deviating from a hypothesis slope of 0 due to that deviation that is due to what the model is describing. Because what you're always testing in a regression is if this is the mean of y, if this is a y bar, to what degree do these data deviate from that flat line with a slope of 0? So this is y equals a plus bx, and in this case, b has a slope of 0. Now, if the best fit line through these data points is this, the sums of squares residual, the sums of squares due to regression, rather, is to what degree does this model differ from a slope of 0, which is the null hypothesis? That's different than saying, to what degree do each of these data points differ from a slope of 0 model? These are then sums of squares residual. Do you see the difference? Oh, sorry. No, I did that wrong. Bah. My bad. Let me go back. Put a bunch of dots in. Best fit line, average value. At this x value, there are two things that you want to know about. One is the difference between the model and a slope of 0. The other thing that you want to know about is the difference between the data point and the line of best fit. Data point and line of best fit. These ones that go from the data point to the line, these are this is how you calculate sum squares residual. Ones that go from the line to the slope of 0 line, these are sums of squares due to regression, the degree to which the regression line differs from a slope of 0. If your regression line that is predicted is
Paul,
not
Hey, Paul,
yeah.
I can't see that board. Too far away.
Oh, you can't see the board. Okay, let me make the board closer. All right. And I can't see my own self. So let's see. Is that closer?
It's got glare from the light.
Okay.
I mean, it's stay away from the top center right
Top
side.
center? Okay.
Yeah.
All right. I'm going to use colors. So let me dig into my packet of tricks here. All right. Can you see those things?
Mm-hmm. Yep, looking
Okay.
good.
So let's say that we have a line of best fit that goes through this data set that looks like this. So that's the line of best fit. The blue line is the mean of y. So in this case, it would be the mean of mass loss in this example, even though this example has the example on your PowerPoint has a negative value, a negative slope. So there are two forms of variance in any kind of an ANOVA issue. One is the variance between each of the data points and the mean of a sample. So you only have one sample here. So the difference between the data points and the mean are the differences between the data points and the line in this case. In this case, the line is the running average of y as it changes with x. So the red is the sums of squares residual.
And that goes from the data point to the sloped line.
To the sloped line, the line describing what the mean is.
And that is the, what is that again?
That's the sums of, that's how you would calculate sums of squares residual. Variation between the data point and the mean.
Which
So
mean, the mean on the mean, see, now we got two means floating around our conversation.
So this is the regression line is the
Right.
equivalent of the sample mean. It's the average of y as it varies with x. So when x is low, the average of y is low. As x increases, the average of x increase, or the average of y increases. As x increases even more, the average of y continues to increase. So when we had, let's see, when we had a regular ANOVA, we would maybe have 3 different treatments. Can you see those over there?
Mhm.
A purple, a blue, and a red. We would calculate the mean for treatment red. We would have a bunch of observations in treatment red, and we would calculate the sums of squares residual by looking at how those values differed from the sample mean. We would have a bunch of values that were blue. We would figure out how those values differed from the sample mean. And we would have a bunch of purple observations. And we would look at how those purple observations differ from the sample mean. Those differences, deviations from the actual value minus the mean squared, that was how we calculated the sums of squares residual. Remember? Is that making sense?
Now in that sentence, you use the word mean, and you don't mean the horizontal line mean. You mean the slope line mean.
Hang with me. Yeah. So pay attention to the ANOVA case first. This is the sample mean taken from the actual observations. Also in this figure is a grand mean. Okay.
Mm-hmm.
Now the treatment effect is the difference between the sample mean and the grand mean squared. Sample mean versus grand mean, and sample mean versus grand mean. This is where we get sums of squares among. Okay, so this is old school ANOVA. You're already familiar with this. Variation within versus variation among. The model that you're testing when you test an ANOVA is a model that basically says the treatment effect is what you're testing with the sums of squares among, and you're having to see that treatment effect as it gets obscured by variation within sample. Now, when you go over to the ANOVA, the variation within the sample is the variation between the value and the mean. This mean is basically the average of the Y values as X changes. So you can think of the line as being equivalent to the sample mean. So the difference between the data points and the line is the equivalent of sums of squares residual, as it is over in the ANOVA case. Y bar here is the average of the Y values regardless of X. The average here for your data set that is in the example is 6.022 regardless of what X is. So one of the ways of thinking of this is thinking of this as the grand mean. It's the mean of the Y values regardless of what X happens to be. In the same way, this is the average of the entire data set regardless of what the treatments are. Does that make sense?
And so where does that show on the?
I haven't done it yet. So if we want to know what the sums of squares are of the model that we're looking at in a regression sense, we need to ask ourselves, to what degree does the sample mean differ from the grand mean? To what degree does the sample mean differ from the grand mean? To what degree does the sample mean differ from the grand mean? To what degree does the sample mean differ from the grand mean? To what degree does the sample mean differ from the grand mean? To what degree does the sample mean differ from the grand mean? These blue lines now are the equivalent of the mean versus the grand mean, mean versus grand mean, mean versus grand mean. In this case, you have as many different entries as you have means. In this case, you have as many different entries as you have data points, but the data points aren't being used to calculate the difference between the data point and the grand mean. They're basically, the data points are basically saying at a particular given X, and the X values are determined by where the data points are. At those X's, how does the grand mean differ from the predicted value of the regression? That then tells you how much variation is there that is due to deviations caused by the model, which is the same thing as saying how do each of the sample means differ from the grand mean in an ANOVA scenario. These blue things then are sums of squares that are due to regression. The fact that the best fit line isn't a flat line of 0, it's actually a line with a slope. So in this way, regression is analogous to ANOVA. It's just that in an ANOVA, the model is looking for variation among the means. In this case, the regression is looking at deviations from the grand mean that are due to the fact that you have a regression line that doesn't have a slope of 0. So when we go and look at the main effect here that we're interested in is how does the predicted value differ from the grand mean? For these values that are close to the grand mean at the middle part of the regression, 5.9, 5.83, these are all close to the average value in the same way that the predicted values are close to the value in the middle. As you move away from that, the predicted values get further and further away from the average value because this model doesn't have a slope of 0. So let me show you that in this way. So I'm going to draw another regression over here. In this case, the slope of the line that is the line of best fit is much shallower. The blue line is still going to be the average of y. In this case, the sum squares residual is still the difference between the actual values and the best fit line. But now, for each of these, the difference between the model and the best fit line still has negative values below the line, positive values above, but these values are all much smaller than these blue values are, which means that the sums of squares regression is much smaller. Small, 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 as opposed to large, large, small, small, large, large. Because these blue values don't deviate from the grand mean, sum of the squares due to regression is small. And now you probably can't see that because I'm in glare up there. These values that represent the sums of squares regression this sums to a small number because each of the values comparing the predicted value to the grand mean, predicted value to grand mean, predicted value to grand mean, predicted value to grand mean, those are all relatively small compared to what they were in this model. It basically means that the regression line isn't describing a lot of the variation between the prediction and the mean, which means that the slope of this line is actually close to 0. And as a result, it gets hard to tell that that slope is different from 0 because this sums of squares regression is explaining very little variation compared to the amount of variation around the regression line. This would be harder to see a significant regression. This is easier to see a significant regression because the variation explained by the last column is tiny as opposed to large. Does that make sense? Or have I just confused the heck out of you? It's so confusing, you guys have all logged off. Anybody there?
It's just kind of a lot right now.
Yeah, it's
Okay. What can I do to clarify it? I feel like I've actually confused you more than clarified you based on the silence. Thomas, did that help or did that confuse more than anything else?
Hey, oh, sorry, I was muted. Hey, well, I went to full screen mode to see your whiteboard, which meant I lost my ability to go to mute, unmute, and lost my ability to see the chart. So I don't know, it's just not very handy. But okay, so in a nutshell, sum of squares regression is the distance from some point on the sloped line to the flat line, which is the grand mean. And that is our old friend, the effect of the treatment. Okay.
And in this case, the treatment is the regression model.
Okay. And we have to pick a spot. We have to pick it somewhere along the x-axis to test it. And we just choose the point where the observations are, but we wouldn't have to. Okay, so that's sum
Yeah,
of
so
squares
we
regression.
choose the points where the observed data are, so that our sum of the squares regression is based on the same number of data points as the sum squares residual.
Okay. And then sum of squares residual is the distance from the data point to the slope line.
Yes.
And that tells us the residual is like the error. It's how far off we were from, how far, I guess, it's how far off our sloped line of best fit, best predicted line, how far off it was from the real data point.
Yeah, one way of thinking of the residual is it's the amount of variation in the data that is not explained by the line. The residual value is the amount of variation not explained by the y equals a plus dx.
And in a graphical way, that's the distance between the line and the data point.
Yep. So in an ANOVA way, we have different distributions, and that, unfortunately, that guy is dying. Let me do this with a different color. In an ANOVA land, we have the mean of the red. We have the mean of the red distribution, the mean of the purple distribution. Each of these is undergirded by observations. So the mean explains some of the variation in the whole data set, but there's unexplained variation due to variation around the means that is unexplained by the mean. So in this data set, we can describe variance can describe variance from the grand mean due to variation of the differences between the grand mean and the sample means. But then there's variation in your data set that is not explained by that. And that is due to variation within the means.
Now we really don't, those little points you just pointed to.
Yep.
We don't really have those.
You actually do have those. This is,
Where are they on the other graph?
this is variation between the individual values and the sample mean.
And where is that up on the top left graph?
Individual values and sample mean.
That's one point.
That's 1 point.
You pointed to a bunch of little points under the
Individual point and sample mean. Individual point and sample mean. Individual point and sample mean.
Okay, then now back to the bottom chart. You show two normal distribution. I don't know what those are, clusters or treatments. Yes. Where are those on the? Where are
there's
those?
There's only one of them because we don't have two different treatment effects. The treatment effect essentially is how does X affect the value of Y. In this case, we had treatment purple affected our response variable and treatment red affected our response variable. In this case, we have two independent variables, one of which is the X value and the other of which is the Y value. So just to continue the analog, in an ANOVA, we have an independent variable and a dependent variable. In an ANOVA, what is the independent variable?
X.
Well, okay, so it's treatment.
Oh, okay.
Treatment A, B, C, and D, and we're looking to see how the individual values are affected by those different treatments. Same thing happens in regression, except now the independent variable is X, and we're looking to see how variation in X affects variation in Y. It's just that now our treatment value is a continuous variable rather than a categorical variable.
Okay.
Does that make sense?
Mm-hmm. Yeah.
So we don't have 2 or 3 or 4 treatments. We have one general treatment, which is variation in X, that we're looking to see how that then affects variation in Y. But it's really no different than giving rats fresh fat versus rancid fat. One of the things that we could do with independent variable fresh versus rancid and look at the dependent variable growth, we could have said that the numerical value for fresh would be 0 or would be 1, and a numerical variable for rancid would be 0, in which case we could say that the X variable has a 0 value and a 1 value, and there is a bunch of data that we could calculate the mean and the confidence interval for rancid, and there are a bunch of data where we have a mean and a confidence interval, and we could actually calculate a regression line between those two things, assuming that 0 and 1 were numbers, not categorical factors. As it turns out, this slope line here would be estimatable. There is also an intercept involved in this. And what we would have is we would have residual variation, which is each of these individual values and their distance between the values and the value of the line. And we would have that here, and we would have that up here. And they would all be at the same X value. They would all be at either 0 or 1. But there's also a grand mean in here. And we would calculate what the grand mean is by comparing this mean to the grand mean and this mean to the grand mean. This would be sums of squares of the treatment. This would be sums of squares residual. Sums of squares residual. It turns out in R's mind, there's no difference between this and this.
Yeah, we've just shifted to continuous variables instead of.
Exactly. That is exactly what has happened.
And it's continuous, but we had to pick some points, and those ended up being our 9
Yep.
data.
Yeah, so in this way, the reason that we get ANOVA tables out of both ANOVAs and regressions is because mathematically, they're exactly the same. The only difference is that when we put a standard ANOVA with categorical independent variables in it, is that the computer assigns a numerical value to those things. There's a section in your textbook about how to code categorical variables, if I recall correctly. I actually have my book here. Maybe it's not in this book, maybe it's in a different book. It's not in this book. In Sokol and Rolfe, which is a book that you do not possess. Let's see. This is kind of an advanced topic, which is why it's at the end of the book. No, it's actually in an appendix. There's a whole section basically talking about how coding variables influences what the results of an ANOVA are. It's not something that you need to know about necessarily, but in some cases, people will actually go through and manually code their variables so that their written variables of fresh and rancid are not coded for with names. They're actually coded binarily with numbers. And the way it's done typically is if you have two variables, you have two columns. The first of these would be 0, 0. This would be variable 1, independent variable 1. This would be independent variable 2. And then this one is coded 0, 1. And you could code this into an ANOVA in R and tell it to actually analyze these two numerical values. And when you ran the ANOVA, it should give you the same answer as if you put in fresh and rancid. So it's treating both regression and ANOVA in exactly the same way, numerically. So that's what those two columns are about. Does that help?
And back at ANOVA, remember ANOVA, we had the within, and that's sum of squares residual.
That's residual,
that's
yeah.
the x minus the x bar. And then we had the among, and that is sum of squares regression, and that's x bar minus x grand mean.
Yes.
Okay. All right.
And in this case, the grand mean is just what is the average value of y regardless of x. The average value of y regardless of the value of x. In your example in the PowerPoint, it's 6.022.
Mm-hmm.
The rest of you, clarifying or confusing?
I think that was good.
Okay, who was that, Chase?
Yeah.
Okay. All right, let's see. What else do I want to do? Did you guys understand the part at the end where I talked about R square?
If you could put it in one sentence, somehow distinguish the difference between significant and the P and a good or bad R squared value.
Okay. There are people who argue that we should not evaluate any statistical model on the basis of p-value. And the reason that they argue against this is that given a large enough sample size, you can prove that any two numbers are different. So when we think about why we do statistics, we're generally trying to ask ourselves, in an ANOVA sense, we're asking, is one mean different from another mean? We're asking this question, is mean 1 equal to or not equal to mean 2? This is the question in ANOVA. Now, if mean 1 has a value of 10.1 and mean 2 has a value of 10.2, that's a really hard difference to see because it's a really small difference. But if you give me enough time and enough money, I can get sample sizes that are big enough that I can distinguish between these two values. So there is a sense, a very real sense in that The p-value that you get, and this is what statisticians argue who think we should go away from using p-values as a decision criterion. They argue that p-value is more a measure of how big your sample size is rather than a measure of how big your difference is. And these people advocate that we would report things in terms of sizes of effects rather than smallness of p-value. This is less of an issue with ANOVA because one of the things about ANOVAs is ANOVAs report the means, and so you can actually see what the differences are the means are, and you also have the estimates of the 95% confidence intervals, so you can kind of make some qualitative judgments as to whether or not you trust that that difference is actually real. And you can also, if you know the system that the person is working in, you can also put that up against your own knowledge and say, okay, if that difference is real, is that difference meaningful? And so ANOVA is actually a little nicer when you look at the result, because you can say, okay, is that difference that they report, is it truly a real difference? And if it is a real difference, is it a difference that I actually care about? Really tiny differences, chances are you're not going to really care about that much. But what happens when you do regression is that you don't really know necessarily what a significantly, large slope would be that would be, for example, biologically significant. And so when you crush a regression with sample size, you can get a significant regression even though the slope value is really, really tiny. Because remember, this is the question that you're asking when you do an ANOVA. The question you're asking when you do a regression is, I have an X variable and I have a Y variable. I have a hypothetical slope of 0, and I want to know, is the slope that I observe different from a slope of 0? This is the observed. This is slope equals 0. Now, I can, if I have enough time and enough money, I can generate a data set that is huge enough that I could detect really tiny differences from a slope of 0. But then again, if it's a really tiny difference from a slope of 0, is that slope difference actually meaningful? Well, that becomes a little trickier because we're not used to thinking about slopes. So generally, the bigger the deviation of the observed slope from a slope of 0, the happier you are about that slope. But once again, your ability to tell the difference between this slope and that slope is all dependent upon sample size. So in the example at the end, which you can see here, this is looking at birds choosing which birds to mate with. So you have a bunch of female birds, they look at male birds, they see that a male bird has a long tail, and they're like, hey, that bird there is really sexy, I want to go mate with him. They see birds with short tails, and they're like, yeah, not so much. So one of the things that might happen over evolutionary time is that you might get a correlation between the length of tails of birds and the birds that they mate with. So females, this is a sexually dimorphic species, females have shorter tails than males, but on average, the question that's being asked is, do females that choose long-tailed males also have long tails themselves, representing this correlation in phenotype and the way they look between males and females over evolutionary time. Well, if evolution was really working on this in a strong sort of way, we would expect two things. We would expect that regression to be close to a slope of 1, and it's closer to a slope of 0.17. And we would expect the variation in male tail length to be explaining quite a lot of variation in female tail length. But what we find in the end is that the regression is significant, and that this researcher can tell the difference between a slope of 0 and a slope of 0.17. That's a really pretty small difference in slope, which is why those lines look fairly flat. So you can detect this mainly because you have 337 pairs of birds that you've analyzed. This is your effective sample size. And as a result of that, you have a lot of power to detect really small differences in slope. So one of the ways that you can assess this is by looking at the R-square value. In this case, the R-square value is only 0.09. So even though that slope is significantly different from a slope of 0, there's a lot of unexplained variation floating around. And so when I first saw this paper back in the mid 1990s when I was in graduate school, I looked at this regression and I said, that regression doesn't really tell me anything, because even though the slope is different from a slope of 0, male tail length doesn't really explain much of the variation in female tail length. So R-square is just another way. So my definition for R-square is, to what degree does variation in the X variable inform you about variation in the Y variable? In this case right here, knowing about variation in X tells you everything about variation in Y. Down in the lower right-hand corner, knowing something about about the X variable doesn't tell you much at all about the Y variable. And so there is a question of, is the slope significantly different from 0? That's one question you can ask of a regression. But the other question that you can ask about the regression is, does X do a very good job of describing what Y is? And that's what R-square tells you. Does that help clarify?
Yep, that's good. Thanks.
Yeah. So this appeared in Evolution, which is a very well-respected journal. And when I saw this, I was like, you know, I don't know that I would have recommended that this be published in Evolution if I was one of the reviewers on the paper, because of the information that is highlighted right here. Normally, I'm of the opinion that you can never have too much data. The one area in which I think you can have too much data is in the area of regression, because you can pay attention to the p-value and think, woo-woo, I found a result. And then you look at a graph of the data, or you look at the R-square value, and you're like, oh, I spent a lot of time gathering data that ended up showing me that I have a slope that is significantly different from 0, but doesn't do a very good job of describing the data that I have. In my doctoral dissertation, I had a chapter where I was looking at the foraging of spiders with different numbers of prey items. It was a very esoteric, theoretical exploration of foraging behavior in animals that can either only handle one prey item at a time or can handle multiple prey items at a time. And I spent so much time and effort measuring the weight of the little crickets so that I could accurately measure how much of the cricket had been eaten by a spider, that my data were very, very precise in terms of what I was actually measuring. And I found that my regressions between number of prey eaten, or number of prey offered to a spider, and the amount of biomass that they pulled out of those prey, I found that between starving spiders for 10 days or not starving them at all, I found significant statistical differences between the regression of the number of prey versus amount of biomass pulled out of those prey. But when you looked at the lines on the graph, you couldn't actually see an eyeball difference between the lines. It was almost impossible to tell whether or not the lines were sitting on top of one another or not. So I had crushed this thing with sample size. I had 400 and some odd samples of this. I had crushed it so much with sample size that I could statistically distinguish the two lines from one another, but I couldn't visually see the difference. And so one of my chapters in my dissertation is these data are significant, and what you can do with them is you can ignore them because they're actually not biologically meaningful. Going back once again to something I've talked about before, which is that there is a certain amount of judgment that is involved in doing statistics and doing statistics well. And with that, we're out of time.
Any
Questions? Tom, you were about to say something?
Oh, a homework, assignment, problem set, anything?
Not yet, not until we get to Monday's material.
Okay.
And also you've got a problem set that's due next week and a write-up to do, and I don't want to load more things on top of you until you've gotten some progress made on things that are already out there.
All right.
All right. Email me with questions, and I'll either get back to you on Zoom or I'll get back to you on email, and I'll see you guys on Monday.
All right. Thanks, Paul.
Yeah,
Yeah.
Yeah,
Take care of yourselves.
you too.
always.